Distinguished guests and fellow researchers, hello. I'm Hao-Yun Chi from the China University of Technology in Taiwan. I'll be presenting our research titled, Applying Digital Twin and XR in a Real-World Residential Renovation. Our research centers on a real-world case study. This project required a full gut renovation. Essentially, we stripped the unit from the developers. Standard layout right down to the bare concrete shell, allowing us to rebuild a truly bespoke, living environment from scratch. Projects of this complexity face significant industry challenges. First, traditional methods rely heavily on manual tape, measurements, and hand-drawn sketches, which introduce human error. Second, there is a massive communication gap. The drawings often lead to misinterpretation between designers, contractors, and clients. Third, and most critically, in complete demolition scenarios, measurement inaccuracies trigger structural conflicts mid-project, leading to expensive on-site corrections. Our research mission was to implement an advanced digital twin and extended reality XR workflow to manage this complexity. Our approach integrates digital twins as the single source of truth with XR technology to bridge the gap between digital design intent and physical execution. A key contribution of this study is the validation of a low-cost, high-efficiency workflow. Instead of using expensive terrestrial laser scanners (TLS), we utilized consumer-grade hardware. For capture, we used Insta360 cameras for comprehensive visual context. For processing, we leveraged Matterport's AI-powered reconstruction to convert 360-degree photos into 3D point clouds without complex hardware. For visualization, we utilized Samsung HMD Odyssey Plus Mr. headsets. Let's look at the workflow. Step 1 is spatial data acquisition. The critical timing here is essential. We conducted high-resolution capture immediately after demolition was complete. This allowed us to capture the space in its raw structural state, documenting beams, concrete columns, and mechanical systems. By doing this, we generated an as-demolished digital twin. This ensures our digital model reflects actual site conditions, rather than assumptions from the original architectural plans, which are often inaccurate. Step 2 is the conversion from digital twin to a buildable model. We process the AI-synthesized point cloud, E57 data, exported from Matterport. Using this spatial data, we reconstructed a structured 3D BIM model. This is the bridge between captured reality and the design process. We developed the interior design directly within this verified environment, ensuring the new layout aligns perfectly with the reconstructed existing conditions. Step 3 is immersive design review. Here, we move beyond flat screens. Using high-fidelity Mr. headsets like the Samsung Odyssey Plus, stakeholders can step inside the BIM model and experience the space at a 1-to-1 true scale. This allows for 1. Design validation. We verify ergonomics, aisle widths, and sightlines instantly to ensure the layout feels right. 2. Immersive visualization. Using old technology, we simulate true-to-life colors and material finishes. Specifically, regarding materials, we move beyond small swatches. The VR workflow allows us to see how marble veins align with wood grains in the full context of the room. We also performed physics-based sun studies to verify how natural light interacts with textures throughout the day. This acts as an insurance policy for aesthetic decisions. Step 4 brings us back to the construction site. We call this the game changer. Standing in the empty concrete shell, we use mixed reality Mr. to superimpose the finished design onto the physical space. This provides the critical capabilities. 1. X-ray vision. Contractors can visualize complex piping and wiring routes overlaid on existing walls. 2. Zero-error layout. By projecting the BIM model directly onto the site floor, we verify critical dimensions before a single brick is laid. This eliminates costly layout errors and ensures the digital plan matches the physical reality. The empirical results from this project are significant. We observed a 73% increase in design confidence, where stakeholders gained certainty through VR immersion. We achieved 85% layout optimization, meaning the vast majority of spatial issues were identified virtually before on-site work began. This led to a 40% increase in decision speed. Regarding design sign-offs, qualitatively, the most valuable outcome was proactive conflict detection. We identified clashes between new HVAC ducting and existing low beams in the post-demolition shell during the digital coordination phase. We resolved these engineering solutions digitally, dramatically reducing on-site revisions and material waste. Traditionally, clashes between mechanical systems and structural elements are often discovered on-site, leading to costly delays. Our workflow changes this paradigm by enabling early identification. As you can see in the diagram, we conducted a digital dry run during the system coordination phase. Specifically, we identified clashes between the new HVAC ducting and the existing low beams within the post-demolition shell, conflicts that were not apparent in the 2D drawings. This allowed for immediate resolution planning. We engineered the solutions digitally before any materials were ordered or trades were mobilized. The result is execution efficiency. By resolving these issues in the BIM model rather than on the job site, we achieve significant cost savings by avoiding rework, ensured schedule protection, by eliminating unexpected delays, and maintain quality assurance by not compromising the design intent to fit mechanical systems. In conclusion, while this workflow is not a universal solution for every project, it provides a strategic advantage for complex renovations. By combining AI spatial capture with BIM reconstruction, we turn unpredictable site conditions into managed data, creating a digital safety net. This approach transforms the renovation process from a stressful gamble into a controlled, predictable engineering achievement. Looking ahead, our research team is focusing on 3 key directions. 1. Automated scan to BIM. We are investigating AI-driven segmentation algorithms to reduce the manual effort currently required to convert point clouds into semantic BIM objects. 2. Accuracy validation. We are conducting quantitative comparative analyses between this consumer-grade photogrammetry workflow and terrestrial laser scanning TLS to define precise error margins. 3. FM integration. Extending this digital twin framework to support post-occupancy facility management. Thank you for your attention. Welcome any questions regarding our methodology.